Awesome. Thank you. So, hi everyone, and welcome to the Kubeflow Virtual Symposium. We are very excited to share something that will change how you develop machine learning models with Kubeflow. So, did you know that 23% of all machine learning jobs fail in production data centers? Yeah, 23%. And that's almost 1 in 4 jobs that waste time and resources before you even know there's a problem. So right now, if you could go to the next slide, please. Yeah, right now, if you want to use Kubeflow Trainer, you need a Kubernetes cluster. That means every time you want to test something, even a small change, you are paying for cloud resources. Think about your typical development cycle. You write some code, you want to test it, but you need to spin up expensive GPUs in the cloud. And maybe you have a small bug in your data loading code, but now you have wasted a lot of resources just to discover a simple mistake. And also, many data scientists may not be as familiar with Kubernetes, or they simply want to develop and test their training jobs locally for a much faster feedback loop. So, why should you have to deal with cluster complexity when you're just trying to validate your training model code? And this creates a really slow feedback loop. So you write code, wait for deployment, wait for resources, then maybe find a bug and start all over again. Every iteration costs money and time, even for the smallest changes. So, what can we do about this? We are proposing local execution mode for Kubeflow Trainer. Instead of running your jobs directly on Kubernetes, you could run your training jobs right on your local machine using container systems like Docker, Podman, or simply via subprocesses. And what's important, we keep the exact same Kubeflow trainer API, so you don't have to learn anything new. You write your training code once, test it easily on your machine, fix bugs quickly if needed, and iterate much faster. This new mode means you spend less time provisioning in the backend Kubernetes. So when something goes wrong with Kubernetes, it can often be difficult to tell why, and it can take some time and organizational effort to resolve the problems. But locally, you can write debug files to your local system, view them immediately, and iterate on problems quickly. You save costs, experiment quickly, and deliver trained models in less time. Yeah, and now Saad will walk you through the architecture of local execution mode and show you a live demo on how this all works in practice. Sorry, Saad, we can't hear you.
Okay. Hello, everyone. Can you hear me now? Am I audible?
Yep.
Okay, perfect. So we will be talking about the architecture overview of the local execution mode. And what we are going to talk about here is we try to minimize the radius blast when we introduce the local execution mode. So we don't have to change the interface quite a lot for users to maintain backward compatibility and to give a smooth transition to the local execution mode. So what we started by the SDK initialization, we minimized the changes to the trainer client instance that you're going to be creating. You just pass local execution mode, you pass local mode or Docker mode or Podman mode, and the default mode will always be Kubernetes, where you will have a local trainer always running and always executing. So if you have Kubeflow trainer installed on Kubernetes, that will where the trainer client will always default to. We also implemented an abstract trainer backend where it satisfies a specific API that any backend or any mode we're going to implement will have to satisfy this interface. So if we're adding new modes, it will always satisfy the same interface to minimize the disruption on the user end. Also, we have reduced and almost no new parameter ingestion. So your parameter ingestions will always remain as it is, no changes at all. The second part of the architecture is the runtime. So for the local execution mode, you can notice we have some some parts are containerized, other parts are using sub-processes or local process. The containerized part will be using the same runtimes as the Kubeflow trainer. It will use the same container runtime images. It will configure the environment to mirror the Kubeflow trainer setup. So we'll configure your local Docker and Podman to use exactly the same setup as the Kubeflow trainer. It's not as scalable as the Kubeflow trainer, but we do our best to kind of name the job, create isolated networking and resources for the local execution. When we go to local process, it's going to be a little bit different, because with local process, there will be like a local runtime variant. We don't need Docker images. We don't need a lot of stuff that's specified in the runtime definition by Kubeflow trainer, because it's like a stripped down version. And it's also hard to manage and limit resources on those. So I will stop sharing for a second now and show a live demo. If everything goes okay, the live demo will hopefully might be a little bit nicer to see. So I have the SDK installed on my machine. I'm using an example that you can find on the trainer examples PyTorch image classification that's available there. So we have modified that a little bit to work for local execution and to demo the local execution mode. Then this is our train function, where we have MNIST training. It's just a couple of convolutional neural networks, forward or like linear layers. This code is already written and provided as an example on the trainer, so I will run that as it is. For local execution mode, typically you would just call the trainer here with no parameters passed, and it will connect to your local Kubernetes instance or use your Kubernetes connection. Now I will be just like passing local, which means I'm willing to use or want to use the local execution mode. So the possible options could be Docker, Podman, and Kubernetes. Then I will list available runtimes. This will list the runtimes from the backend I'm using, which is local runtimes, and I will run a distributed training. As you can see, the train function doesn't have, there is no difference. If you look at the example upstream on the trainer, it's exactly the same thing. The resource limitations, it's a little bit tricky. We do our best to limit resources as per the definition here, but there is no guarantees this will be applied on the local operating system or your local machine, because like it's a bit tricky. So we'll see if we can find a solution for this. And you pass the runtime normally like you would do for your job. Okay. So, and again, to maintain the same interface, we will fetch the logs from the local process with exactly the same interface. So as you can see, it's running on Mac OS on my machine. So it says like here, some redirects are not supported in Mac OS, but I'm using fully distributed on my Mac machine and so on. So let me just recheck this one. Okay, it's completed. Training is completed. I can list train jobs. Here we're working on updating some status and like so the interface is a little bit to be more user friendly. And I can also delete the job which complies with the interface. If I list again, it will stop as usual. So let me reshare again the right slide and go back to Owen, who are going to talk with us about
showing a local execution
sorry,
example.
some implementation details. Sorry, here we go. Owen.
Thanks, Saad. Yeah, so here are some implementation options we have considered for local execution mode and showing the trade-offs between them. So first of all, sub-process mode. The primary advantage of this implementation is that it does not require any container runtime. This lowers the barrier of entry for data scientists who may not have Docker or Podman installed on their machines. However, a sub-process implementation does come with some complexities, mostly because it is quite far removed from the standard Kubernetes implementation. Each training job requires internally setting up a virtual environment containing all of the packages and binaries that would typically be found in a runtime image. And this needs to work on all systems, regardless of the existing state of that system. Feature parity with Kubernetes mode is also tricky, as features like resource limits and multi-node distributed training jobs cannot be easily replicated. Next, we have container-based implementations. So the Docker and Podman implementations are closer to the Kubernetes implementation and can allow for existing training runtimes and runtime images to be used as is. Networks can be set up between multiple containers to simulate distributed training jobs. Resource limits can be honored, and shared volumes can be used for data sets and models pulled by initializer containers. However, container-based implementations require that the data scientist has Docker or Podman installed on their machine, which may raise the barrier of entry for some users. Finally, then, a kind-based approach was also considered and prototyped. This approach internalizes the installation of a kind cluster, installs Kubeflow Trainer on the cluster, and sets up the trainer client to use this cluster. The main advantage of this approach is that it doesn't require replicating any backend logic. Users get the full experience of using Kubeflow Trainer on a kind cluster. The disadvantage of this approach is that it needs to download and run the kind CLI, either as a binary or a container image containing the CLI. It also requires either Docker or Podman and adds the overhead of running a kind cluster on the machine. Next slide, please. So yeah, looking at some of the benefits of local execution mode. One of the key benefits of this mode is that it makes it easier for the data scientists to get started using Kubeflow Trainer. They don't require access to a Kubernetes cluster. They can simply pip install the SDK and start creating training jobs. We hope that this would help adoption and interest in Kubeflow Trainer among data scientist users. Another benefit then is that it provides users with a consistent way of running their training jobs locally and remotely. Data scientists can use the same Kubeflow Trainer SDK APIs for both local jobs and jobs running on Kubernetes, because both Kubernetes mode and local execution mode implement the same interface. Thirdly, it allows users to test and evaluate training jobs locally before running the same jobs on expensive infrastructure. They may want to develop their training jobs locally using a reduced data set and evaluate and iterate on this until they are ready to move to a Kubernetes environment. Next slide, please. So what's next for local execution mode? We're actively looking for feedback from the Kubeflow community. We want to know, what do you think about adding a local execution mode to Kubeflow Trainer? You can reach out to us to discuss this on the Kubeflow Trainer channel on CNCF Slack. We also have some open PRs and an open Kubeflow enhancement proposal, which we have linked in the slide, and all reviews would be very welcome. So in regards to other execution modes, we've discussed sub-process, Docker, and Podman implementations. Are there any other execution modes you'd like to see that we haven't considered? And then lastly, what about the local experience of other Kubeflow components? We know that Kubeflow Pipelines has both a sub-process and Docker mode for running pipelines locally. Are there any other Kubeflow components that would benefit from something like this, like a local execution mode to improve the experience of using Kubeflow locally? And that's it from us today. Any questions and comments would be very welcome. Thank you.
I think we have a question from Kevin, which he's asking about like the Jobset API handles a lot of orchestration logic and how orchestration logic handled with Podman. I think Jobset API handles this orchestration logic for Kubernetes and for the job to be running on a Kubernetes. For local process, for example, it's all like running in a sub process. It's very basic. It doesn't give you like the same fully fledged like feature or fully featured sets that the trainer is going to provide you. For Docker and Podman, it's not going to be as equal as the trainer as well, but it will provide you a good place where you can test and validate your code. And if it is good enough for you, then you will have to, you can use it this way. So there will be an implementation of a small management layer on top of like the clients of Docker and Podman that will like create a network, create the required resources, volumes of networks and stuff, create the containers, label them, and then once the job is completed, it will clean up all of this and return back. There is an initial PR that kind of spins off the containers and spins off, creates a network and so on. But like the cleaning up process and adding this small thin layer is still in progress. I think there is another question. Is there any difference in execution time when moving from this local execution to cloud? I guess there will be, like, it depends on your infrastructure running locally on your machine. It depends also on your machine. If you have a big LLM, your training or fine tuning locally on your machine is going to take a lot of time versus running with a Kubernetes cluster in the cloud. I see Andre is also trying to respond to some of these. Also, we have another question. Kubeflow trainer API integration with Q and Jobset and other multi-cluster CRDs is not clearly documented or exemplified in the KFTO features. I think that's a little bit off topic, but we are working right now on the documentation. I will speak because like I'm kind of contributing to trainer and SDK. So I think there is an effort now to update the documentation and make sure it's well maintained and it supports like all the configurations that are supported. We'll try to cover them. And we appreciate the help. If anybody can like join forces and just give us a hand to document Kubeflow trainer and other component, that will be great. Thank you. Do we hand it over to other people, or is there any other questions? Cool. Thanks very much, everyone. And Chase, we're back to you.